Hello everyone, today we're going to go over the AP Chemistry 2026 free response questions. So the first question says, write the complete ground state electron configuration for the potassium ion K+. So we know over here is our S block, and it starts with energy level 1 right here, and then P block is over here, and it starts from energy level 2 from here. So we don't need any others because K is right here, and if you just follow the process 1s2, next is 2s2, then 2p6, and then you keep repeating 3s2, 3p6, so this is 3s2, this is 3p6, and then finally you get to k, which is 4s1. However, you should notice that it's not asking for k, it's asking for k+, meaning that it lost an electron. So if this is k, it loses an electron, so you get rid of this 4s1, and then you have this final electron configuration. Second asks you which has the larger radius, K plus K, the K plus ion or the K atom, and then to explain. So you can make a Bohr model and then only focusing on the last layer of valence electrons, it would be something like this, where this is K, it has one valence electron because it's in group 1, and then K plus lost an electron, so it's going to look like this. This outer shell is empty, so it's going to be really acting like this. Of course, on these inner stuff, there's like more electrons, but I'm not really focusing on it. However, it's very clear that the K plus ion is going to be much smaller. It is one full electron shell smaller. It has less electrons to hold on to, so it's going to be smaller overall for atomic structure. And they also have the same amount of protons. You should mention that as well. B is a question about calorimetry, and it basically walks you through this process where a student wants to run a calorimetry experiment and then asks you describe how the student can use the temperature readings during the experiment to determine when the dissolution is complete. So the whole idea of calorimetry is you basically have this styrofoam cup that's sealed so that no heat is escaping or entering. And then the reaction you run, or in this case the dissolution, will either absorb or release heat. So your water will either get hotter or colder. So for example, your particles could get hotter like this, if this is temperature, and then your water could get colder. But at some point, they're going to reach the same temperature here. And that's when your experiment's over. Or vice versa, of course. Your water can get hotter and your particles could get colder. The answer to this question would be you would have to wait until the temperature readings plateau. So at first, you see how the initial temperature is 24.5. In about a few seconds, it'll become 23. Then later, it'll become 22. Once these temperature readings start to plateau and stop changing, that's how you know the dissolution is complete. Part C says, use the data in the table to do the following. Calculate the magnitude of the thermal energy Q transferred during the dissolution. So notice how it says magnitude, so we're not really focused on the sign. We just want a number. So we know that Q equals MCAT, this formula right here. And then the mass is going to be the mass of the water plus the mass of the KCl, because both of them are releasing / absorbing heat. So we have 97.5 plus 6.80. That's for M. And then for C, that's your specific heat. It gives you the specific heat, 3.95. And then multiplied by delta T. T final minus T initial is going to be 21.1 minus 24.5. And then you're just going to put this into your calculator to get your magnitude of Q. So when I plug this into my calculator, I get a magnitude of 1400 joules. And keeping track of sig figs as well, because this number right here will give you like negative 3.4, and this has 2 sig figs from delta T. On the AP exam, you can have sig figs that are off by 1, and you won't lose any points. So you shouldn't really worry too much about sig figs. 2 says, calculate the value of the molar enthalpy of solution in kJ per mole for KCl given that this many moles of KCl dissolved. So what you're going to do is first, you have 1400 joules. So that's the same as if you divide by 1,000 to go to kilojoules, you're going to get 1.4 kilojoules. And then you divide by moles because your answer is kJ per mole and you have moles. So you have 1.4 kilojoule over 0.0912 moles gives you 15.4 kJ per mole. And then you also need to consider the sign. So since your solution got colder, that means your surroundings got colder, meaning that your particles got hotter. So your particles absorbed heat, so it's a positive sign. Part D says the calorimeter is not perfectly insulated. Would this cause the magnitude of this to calculated to be greater than, less than, or equal to the accepted value? So first we notice that this whole thing is running in less than room temperature. If room temperature is about 25, this whole thing is less than 25 degrees Celsius. So is heat going to escape or is it going to flow in? Heat in this case is going to flow in. Imagine you have ice. Ice is colder than room temperature, so it's going to absorb heat. Here, likewise, heat is going to flow in. So if it's not perfectly insulated, heat is going to flow in, causing this final temperature to be a little bit higher. It could maybe be 22 because heat entered. So if your final temperature is 22, that means your delta T is going to be a little bit smaller than in reality. Because notice how here we did 21.1 minus 24.5 for delta T, and now we'd be doing 22 minus 24.5. So that's a smaller number. Here we originally had 3.4. This is like 2.5. So your magnitude of Q is going to become smaller because your magnitude of delta T got smaller. Hence, if your Q got smaller, that means that your delta H is also going to be smaller because delta H is simply Q over moles. So to sum it up, heat flows in, causing a smaller temperature change, causing a smaller Q value, meaning a smaller enthalpy. Looking at part E, the student performs a second experiment using the same mass of water but 6.8 grams of RBCl instead of 6.8 grams of KCl. The magnitude of the molar enthalpy is approximately equal. Is the magnitude of delta T in this experiment greater than, less than, or equal to that in the KCl? So H stays the same, and we know that H is Q over moles. We also know that we're trying to compare for delta T. So we could say that this is equal to MCAT over mole because Q equals MCAT. So now we have to consider, okay, we have the same masses. We have 6.8 grams, 6.8 grams, so that's fine. Your specific heats are going to be the same because they're both in water. And then now your delta T, is this smaller or bigger? We now have to consider moles. So originally, we had 6.8 grams of KCl, which gave us a certain amount of moles. Now we have 6.8 grams of this. This is much heavier because RB is heavier than K if you look on your periodic table. So because this is heavier, this is going to have fewer moles. So this thing with fewer moles, if it has fewer moles, but it has the same H, that means this delta T value would have to decrease in this experiment. So it's less than. So to sum up this explanation, you basically say, because they have the same delta H solution and the same mass and specific heat, since we have fewer moles of RBCl, that means there must also be a smaller delta T so that we maintain an equal delta H. Moving on, part F, RBCl has a KSP of 57 at 20 Celsius. Write the net ionic equation for the dissolution of RBCl in pure water. So we're simply going to do RBCl. Probably should include your states of matter. This is KSP, meaning that it's solid dissolving. So normally we have equilibrium errors. Here your K value is pretty big. So if you didn't want to put equilibrium errors, you could probably get away with that. And then this would be aqueous. And then Cl minus aqueous. Straightforward question. 2 says, calculate the molar solubility of RBCl in a saturated solution at 20 Celsius. Show the work that leads to your answer. So first you're going to set up your ice chart and say your initial, this is a solid, so technically it doesn't really matter. Starts at 0, starts at 0. They both have coefficients of 1, so plus x. Final is x. What is molar solubility? Molar solubility is that this change, even though it's a solid, you're technically dissolving a little bit. So this is technically minus x. So if we're able to solve for x, that's our molar solubility. So setting up our equilibrium, we have x times x, which is x squared, equals our KSP, which is 57. So x equals the square root of 57, which is 7.55. Or with sig figs, you can say 7.5. So that's your molar solubility at 20 degrees Celsius. Third says a second saturated solution is prepared by dissolving RBCl in 1 molar KCl instead of pure water. Will the molar solubility be greater than, less than, or equal to? So you could run through the calculations and see that now since we're not in water, we're technically in this solution of 1 molar KCl. That means that this Cl minus is not starting at 0, it's starting at 1.0 from this. So even though this is plus x, this is now technically going to be 1.0, or you could do 1.0 plus x. The math, you can go through all this, but what is probably more recommended and better conceptually is you could say that because of the common ion effect, the molar solubility will decrease. The common ion effect simply says that if you're dissolving something and you're in a solution that has a common ion, in other words, here in this case, Cl minus is the common ion, meaning that you're in a solution that already contains Cl minus and you're trying to dissolve Cl minus, the solubility is going to decrease. That's a fundamental principle. So you can explain that conceptually, or if you run through the math here, you're going to see that x decreases mathematically. Moving on to number 2, it says answer the following question about the chromate ion. First question says, based on Vesper theory, predict the molecular geometry of the CrO4 2- ion. So here we see that there's 4 bonds, 4 occupied areas, and no lone pairs around the central atom. That means that our molecule is a tetrahedral. That's the shape. 2 says, draw a complete Lewis structure for a resonance structure of CrO4 that results in a formal charge of 0 on 2 of the oxygen atoms and a formal charge of -1 on the other 2. So formal charge just says group number minus electrons, where if it's a bonded electron, it's worth 1, and if it's a lone pair, it's 2. So if you'll notice that if you have double bonded like this, and then to complete the octet, you'll need 2 lone pairs, and you do the formal charge of this, the group number of O is 6, and then our electrons, we have 2 lone pairs, so that's 2 times 2, and then you have 2 bonds, so it's -2. So 6 minus 4 minus 2 equals 0. So that's our set. We satisfied this requirement, formal charge of 0 on 2 of the oxygen atoms. So here's one of them and here's the other. For the other, all we can simply do if we want a formal charge of -1, we'll just single bond it. Because now if you complete the octet and you do the formal charge, you'll do 6 minus, now we have 3 lone pairs. So it's 3 times 2, and then -1 bond. So our formal charge is going to be -1. So this is our final answer. For these 2 would have formal charge of -1, and these 2 would have formal charge of 0. So here it says, write a balanced net ionic equation for the reaction between chromate and a strong acid. So we know that chromate converts to this in a reversible reaction. So we're going to first put down those 2. Like this. And then it's reversible, so you could put equilibrium arrows. And then the first step you're going to do is you want to balance your CRs. Like this. Secondly, you're going to balance your oxygen atoms. So here you have 8 oxygen atoms, and here you have 7. So where can we get an oxygen atom? We have water. It says it produces water as well. Now we need to balance these H's, but luckily it says when it reacts with a strong acid, so that's where we're going to get our H's from. We have 2 H's here, so we're going to do 2H+. Whenever you want to check if your equation is fully balanced and correct, you can just add up the charges and make sure they're the same on both sides. So here you have 2 times -2. You have 2 molecules that are -2 charged, and then here you have 2 plus 1. So on this side you have -4 plus 2, which is -2. On this side you also have -2, so we know we're done. The second question says, is the reaction a redox reaction? Justify your answer based on the oxidation number of Cr. So to do the oxidation number of Cr, we'll look here. We see that the overall molecule is -2, and we have 4 oxygens. The oxidation number for oxygen is -2. So we have 4 oxygens with a -2 oxidation number. That's -8. And then our whole molecule is -2. That means that this has an oxidation number of +6. Here we'll do the same exact process, but now we have 7 oxygen atoms, and we said that they have an oxidation number of -2, so that's -14, and then the whole molecule is -2. So we need a +12, and then we have 2 of them, so that means each one is +6. Hence, on this side it's +6, and on this side it's also +6, so our oxidation number did not change, so it's not a redox reaction, because a redox reaction involves the transfer of electrons, and our oxidation number would have to change for at least 1 atom. For C and D, is the reaction represented by equation 2 thermodynamically favorable or unfavorable under standard conditions? Justify your equation with the calculation of delta G. So we have an equation on our equation sheet that says delta G standard equals -NFE. And then this N is a positive quantity of the number of electrons transferred. And this F is Faraday's constant, which is 96,500. So, and we have in equation 2, our E standard is a negative number. So without doing any calculations, we could see that this is going to result in a positive number. And then a positive delta G means that it is thermodynamically unfavorable. On the AP, we probably should do the calculations, but your main conclusion is that you reach a positive number, which is thermodynamically unfavorable. Part D says calculate the number of grams of Cr that could be plated onto the surface of a steel rod with 15 amps of current is applied for 3250 seconds. So I'll show you how to do the stoichiometry, and then I'll show you a nice shortcut equation that I personally use for these type of questions. But for the stoich, you have 3250 seconds, and then amps is really coulombs per second. So we have 15.0 coulombs per second. Our seconds cancel. And then we can use Faraday's number here, where it says 96,500 coulombs per mole of electrons. And then how many moles of electron per Cr? So we can go up and see if we're trying to plate some Cr solid that's over here, and we need 6 moles of electron to plate one of them. So that means per 6 moles of electrons, we have 1 mole of Cr. And then finally it says calculate the number of grams, so we would need the molar mass of Cr, and then we'd plug this into our calculator. So when you put this in your calculator, you should get 4.38 grams. Also notice all the units cancel, coulombs, moles of electron, and then moles of Cr, and we finally get grams of Cr. Shortcut I like to use is this formula where it says the mass of metal plated. In other words, this is our final answer, little m, over the molar mass equals I, which is the current, T for time and seconds, over NF. And if you plug this into your calculator, you should get the same exact thing. You would have I, T, N, F, and big M, and then you're solving for little m. Then you'd get the same number. Part E says in a separate experiment, an iron wire is placed directly in a solution of 0.50 molar of this with pH 1.99. The concentration remained as recorded over time, and the results are presented in figure 3. Explain how the data support the conclusion that the reaction is first order with respect to Cr2O7, 2-. So the number one property of a first order reaction is that it has a stable half-life. 0th and second order kinetics do not have stable first lives. As your concentration changes, the half-life changes as well. But first order, the half-life stays the same. So here we see what's the half-life. To get from 0.50 to 0.25, that would be the first half-life. And that's from 0 minutes to about 20 minutes. And then if you go from 0.25 to about 0.125, that would be the next half-life. Notice how now we're at 40 minutes. It took another 20 minutes. So our half-life stayed the same, meaning that reaction is first order. So you would write, because the half-life stayed consistent over time, then this proves that the reaction is first order. kinetics. The following information applies to part F and G. The student creates a plot of ln this versus time for a trial with initial concentration of 0.50 molar as shown in figure 4. Calculate the value of the rate constant K for the reaction. Report your answer in units of inverse minutes. Show the work that leads to your answers. So the easiest way to do this, you could find the slope of this line, because when you have ln concentration versus minutes, the slope of this line is going to be equal to negative K. So to find the slope, this is just a basic calculation. You can put in your calculator. You can choose any 2 points. I'll choose these 2 points right here. So when I put this in my calculator, I get K equals 0.033 minus negative 1 inverse minutes. And then you would show your work, of course, showing the slope and say that this line has a slope equal to negative K. Part G says the student then runs a second trial of the experiment under identical conditions, but uses an initial concentration of 0.25 instead of 0.50. On figure 4, carefully draw the plot versus time that would be expected for the second experiment. The point at time 0 has already been plotted, which is right here. So this line is going to be the same slope. It's going to be parallel just like this. Oh, that is not a parallel line. But it would be a straight parallel line. I would use a ruler if you have it on the test. And then this is because your K stays the same in first order, regardless of what's your initial concentration. So even though your initial concentration changed, your K value stays the same since it's first order kinetics. And you're able to just draw a parallel line with the same slope because it's the same K. And I would also focus on picking specific points so that I can end up with the same slope. So if I want to make this more accurate, I would go like this. Then connect these points. Number 3 then says nitrous acid is a weak acid that ionizes according to equation 1. Identify a conjugate acid-base parent equation. Be sure to clearly label which is the acid and which is the base. So me personally, I'd pick this as the acid. It's visibly an acid because it starts with H. It's a compound like this. And then your conjugate base is going to be this thing without the H, which is right here. So that's one pair you could choose. You can also choose the other pair where this is the acid and then it loses an H and then becomes this as the base. Either one of those would work. B says a solution of HNO2 with the initial concentration of this has a pH of 2.09. Calculate the value of H3O plus in the solution. Show the work that leads to your answer. So we have the pH and we know that pH equals, we know that your concentration of H3O plus equals 10 to the negative pH. So if we have pH, we can just plug it in to get our concentration of H3O plus. And then putting that to my calculator, I get about 0.008 following sig figs, because pH sig figs only count after the decimal point. 2 then says calculate HNO2 at equilibrium. Show the work that leads to your answer. So here we set up an equilibrium expression where we don't really care about water because it's a liquid, and liquids don't matter when we set up our K. So we have here that it's going to be NO2 minus times H3O plus over HNO2. So we found our answer is 0.0081 for our H3O plus concentration. We can also say that concentration is the same as the NO2 minus concentration, because if you make your ice chart, you're really solving for here. We'll have this be Y. And then this is minus X, and then this will stay Y because our K value is super small. So this minus X doesn't really matter. And then this is 0, 0 plus X, 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 and we have X is equal to 0.0081, and notice how they're the same. So we're just going to plug in 0.0081 for here, and then we also have our K value, which is right here, and then we're going to solve for HNO2 in our calculator. So when I put this in my calculator, I solved that HNO2 has a concentration of 0.1 2 molar. Part C says, in an experiment, the solution of 0.125 HNO2 is heated to this. The new equilibrium concentration is determined to be this. Calculate the value of Ka for HNO2 at 333 Kelvin. Show the work that leads to your answer. So we already set up a K value earlier, and we said that this was NO2 minus times H3O plus all over HNO2. And then they give us our 3 equilibrium values. So if we plug these 3 into this expression, we should get a new Ka value for 333 Kelvin. So plugging that to my calculator, I got 0.00104. And it's unitless, keeping now 3 sig figs because it gave me everything in 3 sig figs. 2 says, is the reaction represented by one endothermic or exothermic? So this is a Le Chatelier principle question, and I'll explain why in a sec. Our original equation is up here. And we're basically saying, is it endothermic or exothermic? In other words, is heat on this side? Are you adding heat as a reactant, or is it a product? So notice how our new Ka value is 0.00104, which is greater than this original Ka value, which was 5.6 times 10 to the negative 4. That means when you heated it up, your K value got larger. And that means that heat would have to be here, because when we added heat, it started to shift this way by Le Chatelier's principle. So since it's endothermic, when you add heat, it's going to shift that way, which is why our K value got bigger. So that's how you'd explain it. You'd say by Le Chatelier's principle, since our K value got bigger when we increase the temperature, it must be endothermic, because when you add heat, the equilibrium shifts right. Part D asks us to identify the pH at the equivalence point given this titration curve. So the equivalence point would be when it's going up here, about halfway into this vertical region. So it'll be about right here at pH 8. It's like where the concave switches. So that's pH 8. Part E then asks us to calculate the molarity of HNO2 in the bottle. So for this one, we're going to need the equation M1V1 equals M2V2, or in other words, MAVA equals MBVB, where this is the molarity of the acid times the volume of the acid equals molarity of the base times volume of the base. This literally just means moles of acid equals moles of base, which we know is true at equivalence point. So luckily for us, we have the molarity of our base, which is 0.16. We also have the volume of the base added at equivalence point. So at equivalence point, we added about 50 milliliters. And then it also told us what's the volume of our acid that we have, about 35 milliliters. So now we have all we need to solve for MA in our calculator. So with 2 sig figs, I get the molarity of the acid to be about 0.23 molar. Part F then says, draw an X in figure 1 to represent a point in the titration where HNO2 is greater than NO2 minus in the reaction mixture. So to understand what's happening here, all we're doing is we're titrating this acid. So we have this acid right here, and we're titrating it using a base. And what we're forming is, this is equilibrium here, what we're forming is NO2 minus plus H2O. So it's asking for a point where this concentration is greater than here. So you can pick anywhere in this whole region, because at this point in time, the concentration of the acid is greater because it's before the equivalence point. Once you pass the equivalence point, then the relationship flips. So you can just put your X like here, for example. Part G says equilibrium constants at 298 are shown, and then it says calculate K2 for equilibrium at 298 Kelvin. So everything here is at 298 Kelvin, so that's good to go. And we just want to manipulate this equation so that we can get this one right here. So we need HNO2 on our reactants. So we have that in this equation. So we're going to keep this equation how it is. So this is what we have so far, and we notice that this condition is met where we have HNO2 as a reactant and we have NO2 minus as a product. What we're only missing now is that our final equation wants us to have hydroxide as a reactant and water as a product. So we can take this equation and flip it, so that when we flip it, we get OH minus on this side H3 plus, we're basically reversing this reaction. Yields, this is 2H2O. We have two of them. So when we add these two reactions together, you'll notice this H2O cancels with one of the H2Os here. So you're left with one H2O. And then this H3O plus cancels with this H3O plus. So your final equation, you're left with HNO2 plus OH minus yields NO2 minus plus H2O, which is exactly our desired equation. So to find the K value for this equation, we simply took the K value from this one, and we kept this equation how it was. But for this one, we reversed it. And so to reverse it, we're going to need to take the reciprocal of our K value. And whenever you're adding equations, you're going to always multiply your K values. So we took the reciprocal of this because we reversed this equation, and then we multiplied these two together because we're adding these two equations once we're done. So our final answer for K2 is 5.6 times 10 to the power of 10. Part H, you can read through the directions. It simply asks, the student claims that methyl orange was the best choice for the indicator. Do you agree or disagree? So here what we want is a pH range that is at or slightly above our equivalence point. So here notice how our equivalence point happens at pH 8. So we're going to need to find something that has a pH range of around 8 or a little more. So that fits this one very nicely. The student that says methyl orange is the best is wrong, because this indicator changes color at around 4 pH. At 4 pH, we're still not done with our titration, so it doesn't make sense to use that indicator. Hence, the student is wrong. Question 4. White phosphorus, P4, can decompose into P2 at elevated temperatures. A balanced chemical equation, Kp expression, and Lewis diagram are given. Part A says the average bond length in P4 molecules is 221 picometers, whereas the average bond length in P2 is 189. Explain why the average bond length in P4 is greater than that in P2. So all it's asking is, why are the bonds in P4 longer than P2? So notice how P2 is a triple bond while these are all single bonds. So triple bonds are shorter than single bonds, and that's because the hybridization of a triple bond is sp. Whereas for here, for a single bond, it's sp3. So notice how this is 50% S character and 50% P character. Whereas here, it's 75% P and 25% S. Because you have 3 P's and only 1 S. So it's 3/4 and 1/4. So because of this, P orbitals are obviously larger than S orbitals. A P orbital is like this, and an S orbital is just like that. So since a single bond has more P character, then it is bigger. And that's why the average bond length is bigger in P4. For part B, all we're going to do is a simple equilibrium ice table or ice chart. So it gives us that the initial partial pressure of P4 is 0.470. So that's what we'll have here for our initial, 0.470. And then this is 0. Then it says some of it decomposes into P2 as it reaches equilibrium. At equilibrium, P2 is determined to be this. So our change here, this is going to be minus x, and this is going to be plus 2x because it has a coefficient of 2. And then we're given that the partial pressure of P2 at equilibrium is 0.630. So that goes here. That means that 2x equals 0.630. That means that x equals 0.315. That means that this minus x is going to be 0.155. So now we have our two values at equilibrium, and all we're going to do to solve for Kp is it actually gives us the expression up here. The partial pressure of P2 squared over the partial pressure of P4 gives you Kp. So we're going to do that here as 0.630 squared over 0.155. So I get an answer of 2.56. Part C says the reaction is thermodynamically favorable under standard conditions only at temperatures above 1500. Student claims that the reaction must be endothermic because it is favorable only at high temperatures. Do you agree or disagree? So for this, you're going to need to utilize an explanation with this equation. So for this to be unfavorable, it must be negative. Here it says for this to be favorable, it has to be negative. Here it says it's favorable only at high temperature. So when this term is maximized, when it's at high temperature, when T is really big, then it's negative. That tells us that this H term must be positive. Because if this H term were negative, that means this term is negative and this term is always negative. That means that G will always be favorable. But because it's only favorable at high temperatures, that means that this term has to be positive, so that when this term is at really high temperature, then it finally overcomes and becomes favorable. So if delta H is positive, that means it's endothermic. That means the student is correct, and we agree. Question 5 says the Lewis diagram of CBrClF2 is shown. Which of the bonds is the most polar? Justify your answer. So out of these three bonds, all we need to see is which of these elements, Br, Cl, or F, is the most electronegative. So the most electronegative out of these elements is F. F is the most electronegative. And because F is the most electronegative, it's going to pull electrons the most towards itself, making that bond the most polar. Part B is a slightly tricky question. It says in this molecule, the FCF bond angle is this, and the BRCCl bond angle is this. Explain the difference in bond angles using principles of atomic theory and Vesper theory. So because the CF bond is the most polar, let's use this diagram up here. Because the CF bond is the most polar, it pulls electrons towards itself the most. That means that there is less electron repulsion near C, because the electrons are all spending more time next to the F. So because there's less repulsion near the C, these two atoms are able to be physically closer together because there's less repulsion. Whereas with Cl and Br, they are not as electronegative. Even though they are decently electronegative, they're not as electronegative, so you still have some repulsion here. And they're also just much bigger in size. So because they're much bigger in size, that also causes hindrance where they're literally too big to be close to each other. So they're forced to be a little bit farther to each other, and hence it has a larger bond angle because they're farther. Part C says Lewis diagrams and boiling points are given in the following table. Clearly identify all the IMFs present in both of these. So this molecule right here is non-polar because it has all four of these are the same atom. They have the same electronegativity. So the only thing here is LDFs, London dispersion forces. For the second one, this is a polar element because we have Cl and Br. Those two do not cancel. And then hence, it becomes overall polar because not all the poles cancel. So you have dipole-dipole interactions. And then everything has LDFs. You do not have hydrogen bonding because there's no hydrogens. 2 says, in terms of the relative strengths of all IMF forces, explain why pure CBrL has a higher boiling point than pure this does. So even though this element has dipole-dipole, which is technically stronger than LDF, the LDFs in this molecule are super strong because all of the atoms here, all the BRs, have tons of electrons and they're big, meaning that they're polarizable. So thinking back to what LDFs mean that if you have this big molecule with a lot of electrons and you take a random snapshot at a random time, there's a solid chance that the electrons are going to be kind of uneven, like some are here and some are here and few are here. They're going to be kind of uneven, forcing a slight negative charge over here and a slight positive charge over here for a split second. And then because this is now negative and positive, you'll then attract another molecule with a negative and a positive. That's all what London's dispersion forces are. So with a lot more electrons in play, you're a lot more likely to get this random distribution where not everything is split evenly. So because there's a lot more electrons here, and the Br molecules themselves are huge and polarizable, that means that the LDFs here are very strong, and hence why it has a larger boiling point than this. 6 says a student performs a spectroscopy experiment with V2 plus ions. Part A says the absorbance is 0.32 for solution, then the absorbance is represented by the particle diagram in figure 2. And then in figure 3, draw if the absorbance is 0.08. So all you need for this question is to know that the relationship between concentration and absorbance, they are directly proportional. So if this increases by a factor of 2, then this also increases by a factor of 2. So because the absorbance went from 0.32 to 0.08, it decreased by a factor of 4. That means these shaded circles will have to decrease by a factor of 4. So 1, 2, 3, 4, 5, 6, 7, 8 here. Decreases by a factor of 4. You'll have 2 here. Part B says the student measures the absorbance of a different solution with an unknown molarity, but the absorbance is higher than the upper limit. The student then transfers 3 milliliters of the solution to 25 milliliter volumetric flask, dilutes it, and measures the absorbance. The absorbance of the diluted is 0.22. Determine the molarity of V2 plus in the diluted solution. So with an absorbance of 0.22, we can go to the graph and find what molarity corresponds with that. So an absorbance of 0.22, that would be this line right here. Going down that line, it reaches about here. This point right here, that concentration is about 0.055, as it's right between 0.05 and 0.06. So the answer is 0.055 molar. Sorry. 2 says determine the molarity in the original undiluted solution. So for this, we're going to use a simple dilution equation, M1V1 equals M2V2. This is our original molarity that we're trying to solve for. Here, this is the volume that we took from our original solution. So we took only 3 milliliters from our original. M2 is our new molarity. That's this 0.055 that we just solved for. And then V2 is our new solution. What's the volume of it? So our new volume is 25 milliliters given here. So we can put this in our calculator to solve for M1, our original molarity of the undiluted solution. So I get that to be about 0.46 molar. Finally, the concentration calculated in part B is lower than the actual concentration of the undiluted solution. The student claims that the calculated concentration is too low because during the dilution step, the final level of the solution was higher than on the mark of the volumetric flask. Do you agree or disagree? So all this is saying is that when we diluted it, this is a volumetric flask. It looks something like this. It has a line here. When you diluted it, the water actually went up to here. So what happens is we're going to have here a concentration that's actually lower than what we think it is for our diluted. So our diluted molarity is going to be a little bit lower than the real. So our M calculated is going to be less than M real for our diluted, because it's more diluted than we actually think it is. Now, because we're getting our original molarity from this dilution, we're literally calculating our original M1 here, taking into account our diluted molarity. That means that our new calculated molarity for original is also going to be smaller than reality. Hence, the student is true. So because this is more diluted than we think it is, we're going to get a molarity for the diluted solution to be smaller than it actually is. And then we use that to solve for our original molarity of the original undiluted solution. And because we use that, then that is also going to be smaller than what it is in reality. So we agree with this student. Question 7 says sodium metal reacts with oxygen according to equation 1, standard enthalpies. Calculate the value of delta H formation for Na2O solid. So we have our final delta H here for the reaction, and all we're going to do is products minus reactants, taking into account these coefficients. So 2 times Na2O, whatever the enthalpy is for that, that's what we're solving for, minus 4 times that of Na solid. Notice how that for Na solid is 0. And then also O2 gas, which is also 0. I'm sorry. So all it is, and then this all equals the total enthalpy for the reaction, which is negative 828 kilojoules per mole. So all this is going to be is 2 times Na2O equals negative 828. meaning that the enthalpy for Na2O is going to be negative 414. So this is negative 414 kilojoules per mole. Part B says an 18.4 gram sample of Na solid reacts with 12.8 grams of this, according to equation 1. Calculate the total amount of heat released during the process. So first we need to see which is the limiting reagent in this. So we're going to do 18.4 grams of Na times 22.99 grams of Na per mole of Na. And then we also have that there is 4 moles of Na per 2 moles of Na2O. 4 Na per 2 Na2O. And then the other side would be 12.8 grams of O2 times 32 grams per mole of O2. And then we have only 1 O2 that gets formed every time you form 2 Na2O. So it's our first step to find the limiting reagent. So we see that this is the limiting reagent because it produces less Na2O. So this is going to run out first. So we form 0.400 moles of Na2O, and it's asking how much heat is released during the process. So we found in part A that there is negative 414 kilojoules per mole of Na2O that's released. And then we have 0.400 moles of Na2O. So we can just multiply these together. 0.400 moles of Na2O times, it's asking how much is released, so that's its total amount of heat, so that's magnitude. So we'll just do 414 kJ per mole of Na2O. Then in our calculator, we finally get about 166 kilojoules of heat released. Finally, part C, lattice energy can be defined as the energy required to separate an ionic crystal into gaseous ions. They have similar crystal structures and the lattice enthalpies are given. Using Coulomb's law, explain why the lattice energy of Rb2O is smaller than that of Na2O. So this is on your sheet, but it says that the Coulombic force, which is the attractive force in ionic compounds, is proportional to Q1, Q2 over R squared. All that means is this is the charge of the first ion, charge of the second ion, and the distance. I'll explain it in a sec. Na2O and Rb2O, we're going to compare the two. Na has a charge of +1, and Rb also has a charge of +1. And then both of them have O, which has a charge of -2. So that's our top part of the equation, just compares the charge of the ions. And here the charge of the ions are both the same, so that doesn't really matter. But the bottom then says R squared, which means that if they're farther from each other, then the Coulombic force is going to be smaller. If they're farther away, then they're less attracted. So which of these is bigger, Rb or Na? Rb is bigger because it's several rows lower than Na. And so Rb is bigger and then O is the same in both. Hence, these two are physically farther away, and hence they have a smaller Coulombic force attraction. Hence, that's why the lattice energy is smaller. Because they are attracted with less force, it's easier to separate them into different ions. It requires less energy to separate them. So that's the end of the video. Hopefully this helped review your answers if you're in 2026 or if you're in the future to study for your AP exam. Good luck, everybody. Thank you for watching.